Great. Well, hey, thanks, Wes, very much. Very appreciative to be invited to the Ames IP Oktoberfest. My name is Thomas Edwards. I'm a principal solutions architect specializing in broadcast, working with Global's customers in Amazon Web Services. And today I'll be presenting on live video in the cloud with JPEG XS and AWS CDI. So a great term that I've heard from our friends in the British Isles is horses for courses. And this basically means, choose the right technology or the right strategy for the specific requirements that you have. So there are many times that you'd like to have highly compressed, high latency video. Where you've got bandwidth constrictions, where maybe perhaps it's going direct to consumer, and where latency is maybe not that important. And that happens to be my daughter on the pony right there. Or on the right side, you might want to go with uncompressed or very lightly compressed video in order to achieve very high quality and very low latency. So this brings us to JPEG XS, which is a low complexity codec that's very low latency and also can deliver very high qualities. So JPEG XS comes from JPEG, the joint working group of the International Standardization Organization, ISO, and the International Electrotechnical Commission, the IEC. And JPEG XS is standardized as ISO IEC 21122. Now, JPEG XS is not the JPEG that you generally use on the internet, which uses discrete cosine transforms. It's also not JPEG 2000, which also is a wavelet codec like JPEG XS, but JPEG 2000 was a very high complexity codec. Now, JPEG 2000 does do a great job of very high quality video compression. It's very efficient, but it really requires an FPGA in order to implement in real time. Software implementations of JPEG 2000 are just not super practical in real time. And that brought us to JPEG XS. And XS stands for either extra speedy or extra slow, depending on who you believe. I don't think there's a formal definition. But one of the goals of JPEG XS was to make it a low computational complexity codec in order to do 4K 60p on an Intel Core i7 in real time. There is a small royalty required for use of JPEG XS, but it is an international standard. So JPEG XS was developed in order to achieve a level of visual losslessness using the ISO IEC 29170-2 testing, which I call flicker testing. And in this flicker testing, you've got a reference image, for instance, on the left, and you've got a compressed and decompressed image on the right, and you flicker back and forth between those two images. And depending on how good the compression is today on this presentation, you may or may not see the compound eye of that fly kind of fuzz out a little bit, right? So the goal of this flicker test is to see if the viewer can determine which is the reference side and which is the side that's been compressed and decompressed. And if you can't actually tell the difference, if you're only scoring a 50-50, then it is past this visual lossless test. So when we look at the latency of JPEG XS, its end-to-end latency in a hardware implementation, FPGA implementation, can be as low as 32 lines. Although in the real world and also in software implementations, we see about 1 frame of latency. JPEG XS has very low multi-generational loss. So if you compress and decompress and compress and decompress, do that for 10 cycles, we only see about a 1 dB PSNR Y prime loss. So it's very stable over multiple generations. Now, for instance, some other codecs like H.264, HEVC, VVC that do more high levels of compression do not necessarily have this quality. They do a great job of 1 cycle of compression, and they're very efficient, but then do it again and again and again, and the artifacts can compound over time. So my personal view is I think JPEG XS needs about 175 megabits per second to deliver a visually lossless HD. And if you compare that with JPEG 2000, it's about 1 extra bit per pixel. Our customers have slightly different views. Our networks who are using JPEG XS, they like 10-to-1 compression. So for instance, 720p 60 would be about 110 megabits per second. Our sports customers are a little bit pickier about visual losslessness. They prefer 5-to-1 compression levels. So that would take 720p 60 to 220 megabits per second. And there's a great white paper on all the qualities of JPEG XS, which I linked to in this presentation. So if you take SMPTE 2110, the Emmy award-winning protocol suite from SMPTE, and use SMPTE 2110-22, which allows you to use constant bitrate RTP payloads defined by the IETF. And then you go over to the IETF, and they are going to have very, very soon IETF RFC 9134, not quite published yet, but perhaps in a month or so, 9134 will be published, defining the RTP transport of JPEG XS, which of course ISO IEC 21122. So combine 2110 with JPEG XS, and that gives you the basis of AIM's IPMX. And of course, as I think some other speakers will be discussing, IPMX has some great opportunities for professional AV applications, and we're hoping that that will increase the amount of fielded JPEG XS equipment out there, which hopefully will bring us some economies of scale. So CDI is the Cloud Digital Interface, and that's delivering uncompressed video, audio, and metadata in the cloud. So CDI allows you to move uncompressed media in the cloud with high levels of reliability. Its expected latency is also low, generally less than a frame. It's based on an open SDK, which is available on GitHub, and it's implemented on Amazon Web Services using SRD, the Scalable Reliable Datagram Protocol, and it runs on our EFAs, Elastic Fabric Adapters. So what does that all mean? If you look at UDP flows in the cloud, just sending straight old UDPs, no forward error correction, no RISC, no SRT, but good old-fashioned UDP unicast flows from instance to instance inside the cloud, 99.9% of the time, you get the full bandwidth you expect and everything's working fine. But every now and then you get a bandwidth dropout. And this is just due to the nature of the cloud. Things happen in the cloud. Sometimes you get congestion hotspots. Sometimes a port may go bad and they need to go fix it. Sometimes you may need to restart a switch. And what happens when that kind of stuff occurs is that it takes about a second for ECMP to reconverge. Let's look at what a cloud network actually looks like. It's known technically as a high radix folded class topology with ECMP. And the diverse traffic across the cloud network can lead to these congestion hotspots. Because there are all these switches out there, there's more opportunity for those switches to be briefly down for maintenance. And for these brief outages, your standard TCP that you'd use for a web page or ABR will work just fine, but your UDP will experience some loss. And let's think about what's happening there. So here's a 1 gigabit per second uncompressed HD UDP flow, something like SMPTE 2110-20. It takes one path through the network to go from instance to instance. That path, is theoretically a fairly optimal path through the network. If a switch, let's say, goes down, it's going to take some time for the network to reconverge to find a new path for that flow to take. And that could take up to 1 second, for instance. Now, I mentioned ECMP. You may ask, what is ECMP? ECMP is equal cost multipath routing. And what this means is when a packet comes into a switch, it's the way it leaves the switch is determined by a hash of what's known as the 5-tuple. The 5-tuple includes the first 5 parts of an IP header, source IP, destination IP, its protocol, whether it's TCP or UDP, and also source port and destination port. It hashes that to try to figure out which way it's going. So for instance, we could have a flow coming into a switch that's destination 10.0.0.3, source 10.0.0.3, destination 10.1.0.5. Its protocol is UDP, source port 2000, destination port 2000. It hashes that into taking the left hand output of the switch. You've got another flow coming in. It's the same 10.0.0.3 source, 10.1.0.6 destination. So it's a little different, same protocol, same source destination port, but because of that little change in the destination IP, the hashing function assigns it to leave from the left side of the port. So that's the way ECMP works in a nutshell. So the neat thing about using ECMP is we can actually take that original data flow, which was like a gigabit per second for uncompressed HD, and we can split that flow into 32 flowlets. And each of those flowlets will have a different 5-tuple. So for instance, it could differ with a UDP source port or something along those lines, something to kind of change the hash of the 5-tuple for each of those flowlets. And that means those flowlets take different ECMP paths. So one flowlet may go like that, and another flowlet like that, another flowlet like that, another, until suddenly you're using almost all of the possible ways to get from the one instance to the other instance. You're going through all these different paths in the network. And what we can do with that now is that we can measure the round trip time on each of those flowlet paths to determine how healthy they are. And let's imagine something happens. So for instance, let's say a switch goes down. The sender can notice that there's a high flowlet RTT on that particular path. And he can say, I'm going to stop using that flowlet. And I'll retransmit any lost data on another flowlet. And unlike UDP, where let's say you have an outage for a second, you've got this huge amount of data you've got to retransmit all of a sudden. Because these flowlets split the total bandwidth by as much as 32, you only have a little bit of data to retransmit in case you take a loss. So the amount you need to retransmit is less, and then you can also rebalance your flows onto the healthy paths through the network. So the scalable, reliable datagram protocol, does it actually work? So we've measured it over a long period of time, and you do not see those dropouts that you see in UDP, the occasional dropouts. Again, of course, UDP works most of the time, but as broadcasters, we need every single frame to make it through our broadcast plan. So, and if you take a look at what happens when a link goes down in the network with UDP, it could take up to a second for the routing to reconverge. With SRD, you briefly have a slight reduction in bandwidth, but very quickly you're able to retransmit any lost packets. You're able to rebalance onto healthy flowlets, and you're back in business. So almost no outage whatsoever. So how does this look over time? What if we take 4 days worth of data here, moving 4K flows over a period of 4 days, and over that entire time, the latency is less than 160p frame, less than 16.6 milliseconds. So it seems to be highly reliable in delivering the required subframe latency. So CDI builds on SRD by providing an SDK, which is available in both a Windows and Linux versions. The SDK is available as an open source project under the 2-clause BSD license. There's no additional royalty. Customers only have to pay for their usage of EFA-enabled EC2 instances. And you do have to have EFA, which is powered by our Nitro card, EFA being the elastic fabric adapter. This SDK really only works within an availability zone, because that's where that folded class network lives. And it's optimized really for EC2 placement groups, and these are groups which are physically located within close network perimeters. For increased inter-vendor interoperability, the SDK has an audio-video metadata layer, and that layer has very similar sample mappings to ST2110. So if you're already doing ST2110-20 for uncompressed video, and -30 for uncompressed audio, and -40 for ancillary data, the AVM layer of CDI will seem very familiar to you as a developer. Just take the same type of sample mappings and put them into CDI. So, some of these concepts at the AVM layer means you can get access to each pixel because, of course, it's uncompressed. You don't have to compress it and decompress it. So you can do pixel by pixel changes in your software. The AVM layer goes a step beyond SMPTE 2110-20 and actually supports an alpha channel for easy overlays in a single essence. CDI is, of course, completely uncompressed. You don't need to spend any CPU or additional effort to encode it or decode it. And also the metadata flows are separate essence. So just like good old-fashioned SMPTE 2110-20-30-40, CDI separates the video, the audio, and the metadata such as ancillary data. So you can split off your SCSI 104s and your closed captions as separate flows. So how are broadcasters actually considering using JPEG XS and CDI? So here's an example of a redundant broadcast dual chain. This is a bit simplified, but this gives you an idea of the flavor of what broadcasters are thinking about. So we've got the AWS cloud, and there's an availability zone within that cloud. On-prem, you've got a JPEG XS encoder, which is encoding your baseband video into JPEG XS in order to transport it. Generally use network address translation to get it over to a direct connect to go into the AWS cloud. JPEG XS goes into the cloud where it lands on an AWS Elemental Media Connect. And you can think of Media Connect kind of like the distribution amplifier or media converter of the cloud. It will take that JPEG XS in, convert it to uncompressed CDI. The uncompressed CDI goes into EC2 instances where things like video mixing, ads are inserted, logos are overlaid. The CDI comes out of that video processing, goes back into Elemental Media Connect, where it's split off. Some CDI will go to direct-to-consumer encoding and distribution for ABR purposes. And some of that CDI may go to a satellite distribution encoding, such as Elemental Media Live, which can encode it into an HEVC StatMux. And then Elemental Media Connect will help take that outside of the cloud and out to your uplink. And in addition, we'll have a complete dual chain. And you'll see all the crossovers between those two availability zones are done using either JPEG XS before HEVC compression or then an HEVC crossover after the HEVC compression. So this provides a very highly reliable situation. If there are any problems in one availability zone or the other, the dual chain continues to operate. And even if there are failures within one of the availability zones, you can use those crossovers to make sure you've got no single point failures. Recently, we did a CDI interop workshop, and this really reminded me of the work that JTNM did in the past with SMPTE 2110 interops. The goal here was to bring in many partners and to have them have their software running on AWS EC2 instances and exchange CDI flows between one another. So in June 2021, we had a bunch of participants. These included folks like Drastic, EEG, Gallery Sienna, Imagine, Matrox, Neton, Nevion, Port9 Labs, ROS, TagVS, TechX, and Telestream. This brought together 25 engineers across 9 time zones, 20 plus applications. The big difference from this between what we're doing here in 2110 interops is unfortunately we didn't get to all go to Houston and go out for barbecue at night because it was virtual. We just had to operate with no fun dinners or drinks or anything.
Well, that's no fun.
I know, yeah. So all the partners were able to interoperate with about 6 to 10 others, and we had over 100 interoperation points. Interoperation also occurred with AWS Elemental Media Connect, as well as AWS Elemental Media Live. And also to make this testing a little easier, AWS developed an open source CDI plugin for the OBS software. And if you're familiar with that, that's free software which allows you to play back media streams and do a minor amount of logo insertion and switching and things like that. So that was used as a CDI source for some of the partners. Others used live streams coming from AWS Elemental in Portland, who sent a live camera shot for using a JPEG XS encoder into Direct Connect. So, at the end of the day, what does this all say? If you want the lowest latency and the highest quality cloud video, I recommend using JPEG XS, which gives you very light compression into and out of the cloud. JPEG XS is an international standard. Anyone can write to it, and it's a very software-friendly codec. So it works well in the cloud, in software, as well as on-prem, where you may want to use a software-based encoder, or you could use an FPGA encoder for the lowest latency. CDI, on the other hand, is uncompressed video and uncompressed audio and ancillary data inside the cloud. It's powered by the design of cloud networks. Their inherent capabilities is what makes CDI work. And CDI is available as an open source SDK that anyone can write to. So if you want some more information on CDI, there's a great paper on SRD, the Scalable Reliable Datagram Protocol it's based on from the IEEE. We've got a GitHub repository for the AWS CDI SDK. There's an AWS website with more information, and also we've got a video from AWS reInvent 2020 from Fox about how they're thinking about using uncompressed for live sports in the cloud. So I want to thank you so much for listening to this presentation, and hopefully we'll have some opportunities for some questions.
Very good. Thank you, Thomas. So just if you could pop back one slide, is that IEEE paper a free paper, or is that behind the infamous IEEE paywall?
I don't know off the top of my head. It may be behind a paywall, but you'll have to check that out.
All right, just curious. So kind of going along that same thing, just personally. So talk to us about how you view the openness, if you will, of CDI versus 2110 and some of the other standards that I know you're intimately familiar with. Is it truly an open specification, or is there something that is peculiar to CDI that can only run on certain specific platforms?
Well, I will say, CDI, the SDK is open source and it's on GitHub. I will say the implementation that AWS uses is AWS specific, right? We have our Elastic Fabric adapters. We've got our Nitro cards systems, which the Elastic Fabric adapter uses. And of course, the scalable, reliable datagram system was built to operate in our network. Of course, any other cloud provider could also write to the AWS CDI SDK. They might want to implement it in a different fashion. I can't really speak for anyone else but AWS.
So in other words, the SRD function, is that so that's critical to the AWS implementation, but it's not required for the CDI SDK to be implemented correctly. Is that what you're saying?
Well, I mean, what I'm saying is that the SDK calls could be implemented in a different fashion, right, than the way that we implement it. So, but the calls are the calls. Right.
So you wouldn't have to implement SRD in order to get CDI working if you're trying to put this on another platform. Is that what you're saying?
Yeah. You'd have to figure out some way to make it work, obviously, but
Sure.
But yeah, you could certainly write it with a different underlying protocol.
All right, cool. That's interesting. So open the floor to any questions. I'm looking here on the chat window. If somebody has a question they want to unmute, that's fine too. If you would, turn on your camera and your microphone. I see Jean has his microphone on.
Yeah, my question to Thomas is, so CDI, it's all uncompressed inside the cloud, and JPEG XS, you're talking about using it to go from the ground to the cloud, but couldn't you use JPEG XS inside the cloud as well?
You certainly could.
Right.
And yeah, certainly, yeah, and that's something you could even do with AWS Elemental Media Connect. You can use that to, convert CDI to JPEG XS and use that, either within the cloud or to another availability zone. Mm-hmm.
Okay, so in your mind, it's not necessarily limited to the edge.
Right, I don't think it's limited to the edge. What I will say is that JPEG XS, when it's placed into RTP and using UDP, UDP can occasionally take losses, right? It can take losses on the internet, it can take losses in the cloud, right? And there are different solutions to try to solve that. What we're generally doing is using SMPTE 2022-7, dual hitless failover with JPEG XS flows. And that way you get kind of the advantages of it's using UDP, but should you take a hit on one of the flows, you can make up for it from another flow. CDI, of course, is very different in that it's using all the different paths through the cloud network. So these are just slightly different ways of addressing the same issue. Of course, with 2022-7, there is some buffering involved as well because you may have slightly mistimed flows coming in, and you need to line them up and things along those lines. And you have to have enough buffer that you're lining them up and still allowing for the hitless failover.
Any plan to put the JPEG XS in CDI, if I should say?
Yeah, I don't have any forward-looking advice for you on that right now.
All right, cool. Thanks.
We know what it's like working for big companies, don't we, Tom?
Yes.
So just another question. Going back to the the SRD and recovering from a failed device. Let's say you are spreading out to all 32 streams. What part of the system is responsible for retransmitting the packets that didn't make it through that failed switch number 32 or whatever? How does that actually work in real life?
Well, I have to admit that I'm not a developer, and I don't know the full details underneath all of this about how much is handled by, for instance, the Nitro system, the EFA subsystem, libfabric, and other parts which are under SRD. But so suffice to say, it gets done.
But it's transparent to the endpoints. The endpoints don't really know that it's happening, or are they made aware of it and they have to do anything to accommodate the fact?
Yeah, when you write to the CDI SDK, you just say move the video, and you're not worrying about any of the underlying transport issues. In fact, one of my peer solution architects, Evan Staton, who, while he's a broadcast expert, he's kind of more of a dabbler in the computer programming like myself. He was able to write this OBS CDI plugin in just a few days.
And so behind CDI, the fact that a node has failed is transparent to the endpoint. Is that
right.
What I hear you're saying?
Okay. Right. And what I'll say out of the interop we did, where we had these 13 different partners doing hundreds of different interoperations with one another, one of them said at the end, we've been spending a lot of time sending flows back and forth, but the one thing we've noticed is we haven't had any loss anywhere. Nobody actually saw any loss during that entire time. So
how do we simulate the loss, right? Is that what he asked? we want it to break so we can make sure our apps don't break. Is that right? All right, that's good. Okay. Any other questions for Thomas? John Hale, go ahead.
Hi there, Thomas. It's John Hale here. I've got a real question that I really want to understand. But where is the timing reconciled for the different JPEG XS flows? What device brings it back in, saying if we're going up and down from the ground to cloud, are we using PTP or are we using RTP timestamps without PTP? So
I will say there is no PTP on AWS. We do have a Amazon AWS time sync service, which is more reliable than your standard NTP. It is implemented using the NTP protocol, but it's not as accurate as, for instance, PTP on-prem. So that is what we have to deal with in the cloud today. In terms of how you align JPEG XS, the on-prem, the timestamps are generally going to be developed from PTP. So you can imagine as you're capturing the video, it's going to be time-stamped using PTP based timing. Once it gets to the cloud, it's up to our ISV software vendors how they'd like to implement lining up the different flows which are coming in. Does that make sense?
It does, yeah. Yeah, it does.
Yeah. And I'll say we really do rely on our ISV software partners to do most of the heavy lifting in the video processing, right? AWS Elemental has a bunch of different services, but we don't have a vision mixer, we don't have an audio mixer, we don't have a logo. Actually, we do have some logo insertion in Media Live, but for broadcast applications, we don't have a logo inserter.
Sure, but have you seen any audio video sync timing issues occurring? Like where things are just too far out to bring it back in, where buffers aren't big enough?
I've not seen that yet. I will say it is early days for CDI.
Sure.
And many of the partners who showed up to the interop, only a few of them have generally available products using CDI. Although there are many out there, EEG, Tag VS, Grabio. So there are definitely folks who are now making generally available software with CDI. But I think for many other folks, they're still kind of on beta code, and they're working through. And we are planning on having another CDI interop later in this year to help everyone enhance their interoperability with CDI.